Hello, everybody. Uh, First of all, let me say thank you to the organizers of this very nice event. This kind of event where you learn a lot, no matter how many years you have been in the field, because it's a good review and also progress, right? So thank you very much to all of you for this opportunity. Speaking after Lucas, it's very nice because actually I could summarize my talk saying, now you know a few basic concepts that is, you can actually probe forces other than following a topography, first thing. And second, very important, if you go sideband, you become sensitive to local interaction, and that is what you are gonna see for next hour, basically. So, tell me if I have to go home or you wanna still listen to that. But I'm trying to make, this topic give some order, but honestly not that much because there is still so many open questions, and I hope that you ask so we can make a list and try to debug a bit in the next few years as well. But by the way, so the talk is photo-induced forces and photothermal expansion. It's part one because class after the break will give you another, we continue. But before going there, let me introduce, 1 second, my institution, where I'll be relocating from the United States immediately before COVID. This is the Italian Institute of Technology. It's relatively new. It's 20 years old. Actually, 20 years ago, they founded the first center that is in Genoa. It's still in Genoa. It's the main headquarters where most of the people are. But then there are 11 satellite centers that came out in the last 20 years, and I'm in Milano. That is a 10 years old center. These are a few features. It's a small institute overall. It's 2,000 people across Italy, about 80 research lines. But we have good features, like 30 startups already, 25 joint labs that are founded by company and the institute, like Leonardo Aeronautics or Bracco Pharmaceutical. These are the kind of labs that are joint labs. And also a good track record of grants from the European Commission. We have 59 ERC grants among these ATPIs. There are 4 research areas. One is robotic, that is more industry-related, and nanomaterials, life tech, and computational, of course. Nowadays, we have heard of even question about artificial intelligence role in science, and this is what these colleagues are doing. We are also thinking, of course, of applying to next generation microscopes. This is where eventually we can go. My research line is vectorial, it's missing an L, nanoimaging, because it deals with light and light imaging in the vectorial character of light, so not just integrated scalar information eventually, but taking care in account what is the vectorial nature. And besides scanning probe microscopy, we also do metasurfaces. And this is one example, for instance. This is a laser crystal. We do lasers, actually, because now we put the metasurfaces inside the cavities. Or we do these other kind of devices that are basically reconfigurable devices based on polymers, but still in the realm of flat optics, because all these is devices that are thinner than the wavelengths, so it's appealing for what is next generation of visors or what is called wearable electronics, because they are thin, light, and with a low footprint. This said, let's go to the topic. So, photo-induced forces and photothermal expansion. What is that? Well, I will change into something like more realistic. That is, optical nanoimaging through the mechanical detection. So basically, photothermal and photoinduced forces has a common approach that is to shine light to the tip sample gap, but do optical nanoimaging without detecting any light. So it's the same exact configuration that you have in your SNOM, NIASPEC, with eventually a parabolic mirror to have to be achromatic and focus light to the tip sample junction, but you don't collect any light. So how you do it? Well, there have been different approaches. I'll try to follow a kind of historical development to try to get an order in what you can find around if you try to type photothermal in Google or photo-induced forces. So the first approach with this is photothermal expansion in contact mode. I also brought my cantilever. So what happens? You are in contact, right? Now you know everything about FM after Lucas talks. So yeah, we are in contact. That means somehow the cantilever has two contact points, right? It's fixed on this side to the chip, but it's also kind of fixed to the surface, right? Now, if you shine a laser, no matter how, with a lens, with the parabolic mirror, to this gap, and then you start to go on and off, right? With the laser, what you can do in this cantilever in contact, you start to excite the oscillation. How? Well, let's go in order. What happens in this picture, at least, in this photothermal expansion? In the first generation, what they were selling maybe 10 years ago now, these are the typical features. So what you have an IR laser that was, at the time, an OPO, okay, and was pulsed laser, 10 nanoseconds. That's it. So the light lasts 10 nanoseconds. With a fixed repetition rate of 1 kilohertz, so it's like hammering to the sample with this repetition rate, a relatively soft cantilever with this nominal resonant frequency of 13 kilohertz. I'm just saying typical values. And then what happened? Well, if you shine such a pulse, and the sample absorbs that pulse, the pulse is short, right? It's 10 nanoseconds. The cantilever doesn't follow that. So what happens if the sample is keen enough to expand under the cantilever now, it will basically kick the cantilever, right, through this expansion. So it will be a shot at the cantilever for a transient that is a bit longer, or 10 nanoseconds, and that will be an excitation of this cantilever, right, like this. And then through the optical level, you can monitor such oscillation, and usually what you do is to follow this, plot this kind of trace where you see the oscillation of the cantilever as a function of time. And you see that since it's a 1 kilohertz repetition rate, the initial kick dumps down, right? Because the other, there is enough time between one pulse and the next to completely dump down these oscillations. But then you have this kind of amplitude as function of time, and you can do a Fourier transform and look at the frequencies that are on that, and pick your frequency of choice. Typically, it's of a mode that is far from the nominal mode. It's 170 kilohertz. But you usually select an electronic bandpass filter of 50 kilohertz to basically clean that from the background. And then what happens? Well, again, if you have a laser like this, you can change the wavelengths. And at each wavelength, you will have something like this. So an initial excitation and and ring down. And both the region oscillation and the ring down length will depend upon the local absorption at that wavelength, right? So you can basically get back an absorption spectrum looking at basically the amplitude of this resonance, okay, that you are exciting. There is something more, but again, now you know it's no surprise. You are in contact, right? And whatever is the oscillation frequency, the mechanical property of this cantilever, now that is in contact with the sample, are different, right? And specifically, there is a frequency shift in the modes that depends on the local material under the tip. So basically, if you also now record this amplitude will depend, you also have, through the Fourier transform of this, you also have the frequency eventually. If you don't compensate for that, you also have a kind of information of the local mechanical properties of the sample. But, you know, even if you don't know, you know, it's difficult to have a sense of this if you don't see it, but if you look at the properties of these lasers, it's really like hammering on your sample, right? You are forcing a cantilever that, in principle, want to oscillate around 30 kilohertz. You are forcing with a shot that is 10 nanoseconds to oscillate somewhere else as well. And so it's kind of low sensitivity. Nonetheless, they published a paper on this, mainly using IR lasers to look at the local absorbance of the material. Of course, the other thing that you can do, you can fix the wavelength and scan, right? So you have contrast on the local, based on the local absorption. They may or may not be related to the different composition of the material. For a review, I would suggest to go to this. There are a few reviews out. One of the most recent is this one, if you are interested. But again, shooting with the laser like this, it's aggressive. And later, so what happens is that Michel Belkin group found out a way that is a bit more, give you more sensitivity. Because if you substitute the OPO with the QCL, eventually you can still change the wavelength of the laser, but eventually you can also modulate on-off the laser with different duty cycles and with different repetition rates. And what you can do is to actually tune the repetition rate to the detection frequency. That means that you avoid the ring down, right? Because the next pulse in will come in time to get another kick to the cantilever and basically make almost flat in amplitude kind of oscillation, okay? And of course, if you compare this with this, and you think that all that you're gonna do is a Fourier transform, and you look at the amplitude of a frequency, this gives you a better signal-to-noise ratio because now you have almost constant amplitude, and that you can use to extract the amplitude at that oscillation frequency, right? Ask me a question anytime if something is not clear.
I have a question.
Sure.
You nicely showed that we take the amplitude of a demodulated signal. Can we also use the phase for something?
Yeah, this is why this picture is here. So again, there is the frequency shift to the material, and this would be very sensitive to any frequency shift. So you have actually to use a PLL to look at the frequency shift. Otherwise, you convolute your material information with whatever absorbance is, and you have mix-up kind of a signal, where your signal will be modulated by the frequency shift instead of the local absorbance. So this is very important. When you try to be resonant with in this technique, you have to not just extract the amplitude, but also follow the phase shift due to the stiffness of the material, and adjust the repetition rate of the QCL accordingly. But this is more sensitive than using an OPO, and the group of Belkin showed resolution in principle down to a SAM, a single self-assembly monolayer of molecules. To be honest, they have gold on gold and this molecule in between, so the signal we are speaking about is kind of enhanced. But nonetheless, they could distinguish the aggregates of molecules using going resonant with the excitation. And there are many, you will find many of these examples in literature eventually, mostly, again, in IR, mid-IR, to try to address or look at components in matrices, like drugs in polymers, matrices, or polymer in polymer, not necessarily copolymer, but like these beads of one material in a matrix of another material. And I want to spend 1 second to say something that I will repeat again many times, because when you approach this technique, also what you find in literature, and mostly what people from companies that sell these things are going to tell you is that they try to classify, right? Scattered norm doesn't work for polymers. This is what you want to use if you want contrast. Of course, after 3 days here, now you know, even if I don't tell you, that's not true, right? Because nothing prevents to do scattered norm on polymers that still have a contrast, right? The important message is very much, it depends on many, many conditions. It depends on the sample, but depends on the tip that you use, the illumination condition, whatever is in between the tip and the sample, okay? So I really don't like this kind of generalization, like this technique works for this technique works for that. That's not true, right? It depends pretty much on what you have, what are your experimental conditions, and especially that you know what you are doing. Otherwise, that is, I think, the point zero, right, to get any information. I think. The resolution? Well, the resolution is still local, right? I mean, it's the tip.
Sample expands the focus.
Yeah, but you are probing with that small tip, right? So it is kicking the cantilever, but at that position.
If you have like 5 micron focus, if you have 5 micron focus,
yeah.
Can you expand more?
Okay, I understand. Yeah, no, there is still a tip enhancement kind of effect.
Okay, so there is a tip
enhancement. Yeah. No, that's, all right. Again, not always, right? It depends pretty much on the material. And this is something that I come back later, because you need a material that is keen to expand in the direction that you are probing, and also have a limited diffusion. Otherwise, whatever excitation you do like that will wash out, right? That's basically what you are saying, right? And that also doesn't give you a resolution, but before resolution, it does not give you signal in that sense, right? Because it's not expanding this direction, it's basically spreading away. Yeah.
Thanks.
Any other question? So the best I can do is to bring my own experience on using this kind of technique. And you will find the results in here. But what I did at the time, when I was at Harvard, that was the moment where, Iscate norm, these papers by Dimitri, by Rainer as well, Pablo and so on, were coming out on phonon polarity on hexagonal boron nitride. But at the time, we didn't have any Iscate norm, so I won't just try. And we had plenty of this material because 2 floors up, there was Phil Kim producing this material. So we took a HBM flake and we cut as a triangle to have some edges. And at that time, I went to Dimitri, that is also co-author of this paper, to do this cartesian norm and have a benchmark for whatever fringes I was eventually going to see using photothermal in contact. And surprisingly enough, you see the same fringes. But again, keep in mind, we're not detecting any light here. It's all mechanical. This is mechanical. Okay, it's through the mechanical mode of the cantilever. So what it is, of course, in this case, you have this phonon polariton traveling in the flake, right, on the surface. And you still modulate the field due to the interference. But at that point, you don't collect the scatter light. You are only sensitive to the local field, okay? That is higher on the crest of the fringe and lower in the valley, right? And this is what is plotted. But now you should ask, through what mechanism, right? Because then the question comes that here you also have the evanescent tail of the phonon polarity, right? The near field. Is that near field eventually coupled to the tip and give you a local force that is what actually you monitor? Or is really that HBN is locally expanded and kicking the cantilever, right? So I tried again, just to be sure, different shape. And interesting also, if you do a wavelength change in a single position, far from any crest or valley, like this is right in the center, right, to probe HBN more, to be sensitive to the field, you see basically the phonoresonance of the HBN. And as you've changed the wave number, you see different space in the fringes, looks really the same. Now, the first thing that I noticed is though that when I ramp up the power, and to me, I mean, the only reference I had is that at some point I could set 1 milliwatt on the laser. I don't know how much was really on the sample. There was no way to access that. But they say high power. But again, this is an OPO 10 nanoseconds. This is not even a QCL. I'm just bombarding this HBM flake with these pulses. And again, in this shape, you see the fringes, but you see in topography. Okay, so there is at least a crosstalk with this power on the between the topography channel and this mechanical detection. Okay, that means we are going really non-linear. But even without, when I switch off the laser, I can see that the flake is a bit damaged on the surface. And eventually, you can even see something that resembles the original field distribution inside, still there, right? Modified forever. Now, what's going on? Honestly, it's difficult to understand if it's more a local thermal expansion or was the evanescent tail of the phonon polariton to couple to the tip. Also because HBN is not an ideal material for that, because it has a kind of weird thermal properties, because it shrinks in the basal plane and expands in the orthogonal direction.
What about the possibility that the tip is expanding? I remember from the old times, people tried to do near-field ablation, shooting with laser pulses on tips, and one could see that the materials was modified, but in the end it turned out that it was the expansion of the tip that was then ramming into the sample. So now if you come with an evanescent field, hitting the tip apex may expand a little bit, and that would give change in the topography. It would also hit the sample, and eventually that's the reason why the sample is destroyed. I don't know, is that considered in the field? Expansion of the tip itself?
Yeah, I mean, it may still be, right? But this is mid-IR for the tip, so I would expect that more even in the visible, right? I cannot exclude anything, honestly. This is all that you get, right? You have mechanical amplitude that you are monitoring, and that's it. You have no other information in that. And as I'm saying, as we show in this other paper, but this was more for the structure of HBN than for the thermal, but we indeed did some photothermal in contact. HBN has this coefficient of expansion. That means it's keen to expand vertically and not in the plane. To go in the direction of your question, something that we tried, because the topography artifact is huge here, right? You see exactly the same. But then we said, okay, but as Lucas would say, there is not just sample at tip, right? There is something between. And my suspect is that actually what is contributing is the water that we don't control, the humidity. In either the meniscus or also in interlayer water of this sample, because actually after we annealed the sample, we couldn't find again this kind of effect. So eventually, I guess it's a contribution of everything it's there that is eventually mid-IR absorbing and contributing even in the crosstalk between the channels. That way was reduced a lot. Like we couldn't see this kind of effect at that point. Questions? Okay. Now let's go to photoinduced forces in tapping mode. Oh, first of all, just because it's tapping, it's more gentle eventually, right? It stays less in contact with the sample. You have other parameters to eventually adjust than when you are in contact. What is the description? So this was, as you see, photoinduced forces, like this kind of microscope or approach was introduced by Kumar Vikramasinghe. Then also started a startup, is Molecular Vista, selling these microscopes. But again, the configuration is the same of your NIASPEC, a mirror that focuses light to the tip sample junction. Now, analogously to the description that Rainer did in the past few days, this light would locally induce a dipole, right, in the tip. Then you can think of an image dipole in the sample. And then at this point, for scatter norm, you develop saying there is a effective polarizability that has the information of the tip, the sample, and the environment. Likely, if you scan, eventually, all that is going to change. If you do it correctly, it's the information related, the optical parameter of the substrate, and you have hope that finally you have high resolution image of the optical properties, local optical properties of the sample. In this other picture, you say there are two dipoles, they interact each other, there is a force that is induced by the fact that the tip is illuminated, so it's photo-induced. But before going there, I need a bit more of AFM to how you detect that. It is to consider the cantilever that has, as a mechanical oscillator, has a base of infinite eigenmodes, right? So usually in tapping, use this. But there is also the second. I cannot do the excite the second eigenmode as I look at it. But now you should tell me why I can't, because this looks pretty similar, right? But there is a difference, the length in this case, right? Even if they are same section, same material, the length. The length here sets the spring constant of these two elements. That's why this is more rigid, and this is less rigid. That means that the eigenmodes are shifted toward smaller frequencies than these, and that's why eventually, I can do it. you have the second mode. But by the way, why I'm telling you this, not just for fun, because you have another thing that you have to consider when you are trying to do that later is the bandwidth of your microscope. Okay? It's not obvious that you can use this technique if you don't have enough bandwidth, and we see in a second. So again, we have infinite eigenmodes, but let's stop at the first two. This that goes up and down, and this that has a node in the center. It is a second eigenmode sketched here. And they have two different frequencies, and never be confused between eigenmodes and harmonics. They are two different words, right? So eigenmodes are, first of all, since they are orthogonal, there is virtually no crosstalk between the eigenmodes, right? And the frequencies are very different. This is a table taken from this review by Ricardo Garcia. So you see that if the first eigenmode has this omega 0, let's say that is, whatever, 300 kilohertz, typical number. The second eigenmode is at 6.3 close. The first, means it's close to 2 megahertz in that case, right? And the third eigenmode is higher, and so on. And also, look at the Q factor. As you go higher with the mode, your Q factor increase, and also the stiffness, the effective stiffness of the cantilever increases by a lot, right? It's 40 times the first mode, and 300 more times in the third eigenmode, right? This is to keep in mind. Now, you may ask, how can I find these eigenmodes? Because when I buy a cantilever, I look at the back, and I see one frequency, right? That's omega 0. That's the tapping amplitude, nominal tapping amplitude, like this. Well, you can do it with the thermal tune. That means you don't excite anything. Just because we are likely not at 0 Kelvin, the cantilever is still vibrating. If your sensor is sensitive enough, even without driving the excitation, you can read out the excitation and actually plot the modes, right? So this is the first, and this is the second. If you see this is a medium soft cantilever, 75 kilohertz, that means the second mode is around 400 something kilohertz. And since, at this point, you know that we are somehow gonna use both, this is what I was telling you about the stiffness and the bandwidth of your controller, because now 75 and 400 are eventually within 500 kilohertz. So even a controller with a bandwidth of 500 kilohertz will do we see both. But if this shift here, 300 kilohertz, 6.3 times 300 kilohertz is close to 2 megahertz. It's not obvious that your machine has it, right? So pay attention, because otherwise you are looking for ghosts, right? Because simply they are not there, they're not detected. That's why I'm telling you all this. Now, what are we gonna do of these two modes? Well, again, the picture, according to people that introduced this, is that you have two dipoles. Now you have forces due to the two dipoles. And you can see also in a different way, like Rainer the other day pictured the effect of the sample to another dipole in the tip, right? And of course they are gonna compensate. But if everything depends upon this external illumination, now if that light is modulated at some frequency, also that effect is modulated, right? Whatever it is. Now, the common picture, describes this as two forces, one called local because it goes as the tip sample distance, not linearly, and one that doesn't depend really much on the tip sample distance, that is a non-local kind of force. now, again, now you have to decide what's the frequency that I'm going to use to modulate this interaction, right? And in principle, you can say, okay, in principle, I have two modes here. I use the first mode to follow the morphology. And the second mode, I don't put any feedback. I just read whatever local interaction it is through the second mode. Actually, usually, you approach and follow the morphology with the second mode. That's because, as I show you, it's much stiffer, much higher Q, and it allows you to have very small oscillation amplitude to use and be very close to the sample, where whatever local interaction is most of the time. So let's assume this. You approach with the second mode and follow the morphology, and you don't put any feedback on the first mode. That means whatever local force you are creating is going to change the oscillation of this first mode. So now you have to pick a frequency or modulation frequency for the laser that you are shining there. And you say, oh I'm very smart. I maximize that by hitting at the frequency of the first mode. And if you pay attention to what Luca said, right, before, you will say, no, that's not the way, right? Because it's a direct modulation. And actually, I want to show you something that you can do yourself with your NIASPEC snob. If you do thermal tune, right, you put the driving piezo at 0 and you sweep the frequency around the oscillation of the cantilever, the first mode, you eventually will see these. Depends, how your machine is performing. But by the way, this is, and what is the stiffness of the cantilever. But anyway, you see something around where the first mode is supposed to be. Now, if even without sample, okay, you just shine another laser, the laser from the parabolic mirror, onto the tip at that frequency, without driving anything with the piezo, you see this. So you are light driving the first mode, or you say you are thermal driving through the absorption of the tip. It's actually it's another way to drive the cantilever oscillation. It's called blue drive by Bruca. It's an alternative to the mechanical transferring from the piezo that can help eventually to reduce the signal, to improve the signal to noise ratio in some measurement. But I want just to tell you that, of course, that's not the way, right? It will enhance whatever background from the cantilever it is. And so the solution is sideband, again, as Lucas was telling before, for completely different techniques. So I'm not saying basically anything new under the sky, right? Now, if you modulate at omega m, that is not omega 0, but a sum of the two or the difference, doesn't matter that much, what happens? Well, you are not directly exciting anything, right? Because you are off any resonance. You are inside the band excitation. But what you are producing when you are, since you are close to the sample and you are tapping, is a frequency shift of the resonance, right? Because you are switching on and off anyway an external force, whatever it is. That means that when you modulate omega m, this resonant frequency of the mode that you use to read the information is doing this. It's oscillating, right? In and out from what is the original frequency. So omega become omega m at the rate of omega m. Omega become omega prime at the rate of omega m. But this shift depends, again, by the gradient of the force. And if you do the gradient of the force, you basically minimize whatever force doesn't depend on the distance, right? And so you clean up your detection from the background. So this is the way. You do sideband modulation. Now, the question comes again. Is this thermal or it is optical? Honestly, the technique doesn't tell you if it's a thermal or not. Either that is called photothermal or it's called photoinduced. You have no clue a priori of whatever is the phenomenon, because you are modulating and you are detecting with the lock-ins, and that's it. But nothing tells you that it's thermal or not, also because whatever kind of theoretical derivation of that you try, you start from this, right? That is a forced oscillator. That's it, with the force that depends on the position and the velocity, right, of the tapping. And that's it. And then, unless you are really like making something really tapping hard, that you enhance the nonlinearities, you develop this in a series, a Taylor series, with the first term is the constant, non-local force, because it does not depend by the distance, and a gradient of the force. And this, I'm not doing any hypothesis, so if it's a thermal or if it's optical, because then if it's thermal or optical, it depends how you write this force. And in literature, you find people that develop everything from here saying it's a thermal, and everything from here saying it's optical. But I don't have a solution in that, right? It depends pretty much, again, by your sample, your tip, your illumination. Of course, if you have a polymer that is absorbing very much, a lot, at a specific wavelength, and has a relatively high thermal expansion coefficient with a low diffusion, most likely the thermal contribution is big. But if it's eventually plasmons or phonon polariton in a flake and you are low power, I cannot tell you if it's a priori, if it's the local deformation of the sample, if it's the evanescent tail of the sample. You have to have a feeling by yourself. I mean, it's really difficult. But the starting point is the same. That's my point. And again, I want to bring my own experience, how I tried to debug, at least in one case, if it was more optical or more thermal, but actually this opened other questions that, but it's the way to progress, right? You try to understand. So in my case, what I try to do is to prepare a sample, ad hoc sample, that is islands of titanium dioxide that have refractive index of 2.5, something like that, indivisible, in a matrix of the ZEP. This is the EBL photoresist we use for metasurfaces, with the aim of having a flat surface, okay, where the only thing is refractive index contrast between the ZEP that is 1.6, something like that, and the titanium dioxide indivisible. I was working at 532 nanometer. Actually, if you do this process, that is how we do also metasurfaces until a certain point, you end up with not a perfectly flat surface, this is a section, but with a shallow hollow of 20 nanometers here. This is due to the sun conch effect on the etching of the titanium dioxide. This is to say that if you look then at the topography of this sample, it looks like this shallow 20 nanometer kind of hole. But material side and refractive index contrast side, if you do at the SEM, you have this contrast because the titanium dioxide is a square, is not this hollow. Now, when you do tapping mode for the inducible force, or tapping mode mechanical detection, let me call it like this, without saying if it's thermal or optical, you get squares. That to me means that you are sensitive to the refractive index. Also because titanium dioxide, and I think I have this number here, if you look at the transmittance of titanium dioxide and ZEP at the excitation wavelength, they are almost transparent, both of them. And I tried to, for the metasurfaces, to see how robust it is and to focus a couple of watts of light on the metasurface device. I couldn't modify it in the optical function, so it means in nanometers, right? So I can believe that the contrast in this case is not a thermal expansion because overall, the amorphous titanium dioxide, it's not that keen to expand. But then you will say, that's interesting. Then if you are so confident that this is all refractive index related, also this scale bar has to have a sense, right? In the sense that I'm saying that the titanium dioxide shows a lower signal, whatever, than the ZEP. Can that be quantitative and say, okay, now I know that at least that ratio should be the same of the refractive index? Unfortunately, and that is where opens more question, but only if you go deep in it, is that let's take this other sample. This is a Cove slip with some random particle coming from production. These are the Cove slip that you buy. And unless you clean it before you do any deposition, they come with some particles, right? Now, you do photoinduced force microscopy, 532 nanometer, with a set point of 81%. And you see this contrast. It's a nice contrast. You see gaps that are 5 nanometers, so cool. But then you try to be quantitative. You say, okay, now I try to go to this guy. And what I do is to change the frequency of the excitation and change also the demodulation to see how it look like. And you find the blue curve, okay? Again, here is the modulation around this first mode of the detection is with the first mode of around 300 kilohertz. These are where these numbers come from. But then, and you go to the Cove slip substrate, you do the same, you find the red, right? And that means that with this set point, basically they are overlapping each other. Right? That means that whatever you set your demodulation frequency in the lock-in, you get this contrast. But now, if I push more toward the sample, and I do the same on the two elements, the two curves are going to shift. And this is the material component that is in that. Is due to the fact that they are two different materials eventually. And now, since you decide where you want to demodulate, if I stay on the red curve, I will have always a higher signal on the Cove slip than with respect to the particles. If I stay on this side here, there is no way that happens. It will actually flip the contrast. And if I decide to stay right in the center here, where these two signals cross, you actually minimize the contrast. This is to say, of course, there is the material component that is convoluted with your excitation in that sense. But nonetheless, in literature, you find example of applications. It was mainly from the group of Wikama Singh and Eric Potma. For instance, pump probe, in the sense that they actually use two delayed pulses. And basically, the frequency, the sidebands is in the difference in the frequency modulation of the two. So the difference signal is at the excitation frequency, and they show some contrast. The main point of this paper is actually that if you do the pump probe delay optically, as you would do normally, you find this kind of exponential decay of the signal that has the same kind of trend if you do with this photoinduced force. It was toward the idea that this is photoinduced force in this case. Also, they show that since they are in transmission here and they are focusing with high NA a beam, they have a longitudinal component, and they basically show that the signal, basically, if you just scan a Cove slip, resemble the longitudinal component of the field that will couple to the tip. Or in terms of Raman, what they show is basically it's coherent Raman scattering, where they use they excited and they put excitation also with another wavelength on the elastic scattering at two different frequencies. So it's the Raman shift that is modulated at that specific excitation frequency. And they show a spectrum that they say they resemble what is actually the Raman peak of these molecules, and as well contrast. So it's all based on the assumption that you have an optical force there. And of course, at that point, you can do also with antennas, right? These are plasmonic antennas in metals. Or I did again in HBN, right? I produced this kind of image saying, this is what you get with scattering now, amplitude. And this is what you get with photoinduced force microscopy. So the difference between this side on this HBN disk is that here you collect the light and you do cytoheterodyne. Here you don't collect any light and you do it mechanically. And the amplitude signal look like goes in the direction of the PFM signal. And this opens a bit some more questions that I will give you in a second. I think, do you have 5 minutes yet? Not? Yes? Okay. Now, the title of the talk is Photoinduced Force and Photothermal Expansion, right? Now you know that maybe the question is photoinduced or photothermal expansion, and basically it's like asking, are we detecting oranges of lemon? At this point, I think that the more honest answer is that sometimes they grow together. This is really happening. It's a tree with orange and lemons, and this is more or less what you can get out of the approach, right? Because again, when you buy the technique, either that whoever sells you says that it's thermal or photo, is the same exact technique. You modulate a laser, you use the first and second eigenmode, you demodulate at one or the other, and that's it. Okay? So you don't know a priori if it's one or the other. Of course, people tried to go in favor of one or the other. So there is one paper from Markus Raschke, for instance. He tried to basically prove in this paper that it depends very much on the symmetry of the spectrum that you get. If it's symmetric, that means that it's more absorption, right? Because K goes symmetric. If it's asymmetric, it will resemble more the real part, and then it goes more in the photo-induced part. If I have to look, that's why I plot my image of saying that scattering is now amplitude was the same in that case of HBN to the photo-induced force, because that would be the real part, right? If you assume that in that case you are probing somehow the real part of N that looks like going in the direction of the PFM. Of course, there is also the other group that was trying to go more in the photo-induced, saying the main point here is that if you do these force distance curves and you don't modulate, you don't use both modes, but basically you have both forces, the local and non-local, at some point, one is overcome the other. So you have this green kind of trend. But again, this will pretty much depend on what is your sample, your illumination, what is your environmental condition, what is the wavelength that you are using. As Raina pointed out, if the tip is making a contribution or not, just in terms of absorbing, right? So again, I think the most honest way to call it is that you do a mechanical detection. I don't even call it photothermal or photoinduced, because technically, when you do the technique, you are doing the same thing. Then if it's thermal or not, or photo, depends on what you are doing. But now all this is to say, okay, but I'm confused. This is a school. I should give some hope, right? It's not that you just do measurement and that's it. There must be a reason. Okay, so let's try to point out where I found it useful to use mechanical detection against of using scattering. By the way, now you have that implemented in the NIASPEC, right? So I mean, you can do also that. I comment one thing on that, but later. So scattering norm gives you the unique possibility of retrieve amplitude and phase, right? There is no other way. You have the complex field, and you saw the last few days how having both is important, even just to debug artifacts. But beside that, you can also do this, right? In the sense that you look at the complex information, and you can even follow the evolution of your field that is propagating these phonon polaritons in HBN. This is HBN resonator. Now, where I found that it's useful is in the hyperspectral imaging. Because, if you want to do a real hyperspectral image, where really, I mean, you keep the spatial stepping, so you do 500 by 500 pixels in an image. With scattering norm, you will do that through Nano FTR, right? But try. I mean, the pulse norm has to handle an interferometer, do the Fourier transform. You have an average on each single point. It means that realistically, how much? 100 points? You collect 200, but not 500 by 500, right? With this force, like this technique, what you do at each point, if you have a QCL that can work where you can change the repetition rate and the frequency, the wavelength, you sweep the wavelength, at each point you get a spectrum. Okay, it's quite stable, it works. These are bunch of resonators in the first and second Australian band of the HBN. And you see that as the wavelength number increase, the resonance shifts to the next larger resonator. On the way back, this is the contrary on the second Australian band due to the sign of the epsilon. And this is also MO03 that, I think tomorrow you will hear much more from Pablo. But this is to say, it may complement the scattering norm, because if you want to do theta heterodyne, you need a CW source, and QCL have some limited chip on that. If you go to something that is parsed and still QCL, you have much larger choice. And this is what we did here. We complemented with the PFM, the detection of first, second, and further Australian band of MO03, where the scattering norm basically is these blue dots. Due to just to this difference, technology difference, right? Maybe in 2 years you will have CWQCL commercially available that cover that band, but if you can do any other way by yourself, it's also fine. This is also the message. Now, before I conclude, I think time is over. Just a comment about the NIASPEC thing. So I think it's correctly implemented, and you even have the PLL that follow the frequency shift, so that you get rid from the material component. But take care that if you have to plan an experiment, all that the NIAS norm so far gives you is a TTL. So it works for diodes, where you can plug the TTL and modulate. It can work for QCL, but if you have your laser, let's say titanium sapphire, where you cannot plug a TTL and make it modulate, you have to use an external modulator. Eventually, you have to think how to do it. For instance, we are doing it, but we need a wave function generator that do this, and we have to make it communicated to the controller to synchronize the acquisition. Just this comment, because again, it's a school and mainly on the NIASPEC machine. So if you plan it, take care of the fact that you only have a TTL if you want to try to do that. And with this, I would like to thank you for your attention.
Thank you very much for a great lecture. And short question? Okay.
Thank you very much for a nice talk. Whenever we have an interaction that changes, the Q value changes if we cantilever. So whatever you do, photo, you name it, do you know how much the Q value changes? Can you go for larger Qs? Can you go even for smaller Qs? So to really tune on that.
Yeah, no, so what I can comment on that is that also the first mode and second mode Q are very different, right? And now you can decide to follow the morphology with the first mode and use the second mode as a detector or vice versa. With some sample, that matters. It also means that intrinsically you have different Qs. With others, we cannot really appreciate any difference. This the closest, because we never did any systematic study on that, but that is anyway a hint if that Q may matter or not, actually changing by lot, just not tuning, right?